everyone, this is Dan at SPE Motorsport. On this week's product spotlight, we're going to be going over our 2020 plus GT500 blower pulley options that we have. We're also going to do a segment this week that's a little bit different than what we normally do and kind of show you a little bit of the behind the scenes and the process that we go through with these pulleys, or the blower drive pulleys for that point. We'll basically go over what we have here on the table as far as our idler options and our replacement blower pulley options, and then we're actually going to go to the other shop and show you kind of the engineering aspect of it and some of the nitty-gritty details. Alright, so on the table in front of us here we have our pulley packages, which if you would purchase a pulley from us, they are available separately, so you can buy individual pulley sizes, so you're not just locked into one. The package is going to come with the pulley, the hub, hardware, and the blower tools. You have a holding tool and a snout tool, because our blower pulley hub actually has a specific tool machined for it, because whenever we design the hub as light as we possibly could. So by not having a drive nut on the end of the hub, we were actually able to remove quite a bit of weight from it, which obviously gets rid of rotating mass. The hubs are available in stainless and titanium. Hardware is also available in stainless and titanium. So we do a raw stainless steel style bolt, and we have titanium in black, bronze, green, and blue. Those are all available on the site separately as well. And other parts that we make for the GT500 that utilize similar bolts, including other products that don't even just deal with the blower itself. We're actually able to color coordinate your bolts under the hood of the car, so you can color coordinate your blower bolts and all the other stuff, which that's just a completely a physical appearance thing. It doesn't do anything. So moving down the line here, we have our idler pulleys. Our idler pulleys, we have a static or a stationary fixed idler. And then we also have an adjustable idler, you can see here on the blower. The adjustable idler is great for the person that is going to be changing pulley sizes a lot. So if you're tailoring your car to different types of racing or power levels, the adjustable idler is great, because then you might be able to take one size belt and make it work for different sizes, pulley wise. So that's very convenient for the customer. If you're running just one size blower pulley and you want to get your belt belt length dialed in, the easiest way is just to get the stationary and just get your belt length set, and then you're good to go. Back to the blower pulleys. As I said, you can even actually buy the tool separate. The hub can even be purchased separately, so if you ever wanted to upgrade from a stainless hub to a titanium, you can do that later on. But basically, yes, so the pulleys are available in multiple sizes. So you have the 3.2 all the way down to a 2.27. The 3.2 pulley is for the customer that wants to spin the blower slower than factory, because the factory blower is around like a 3.05, I believe, pulley size. So the 3.2 is actually going to turn the blower slower, meaning it's going to put less heat in the blower assembly. So if you're road racing, autocrossing, doing like more of a long, prolonged type of race of some sort, or driving, it puts less heat in the motor, less heat in the blower, and actually probably add some longevity, to the life of everything, including the engine and the blower. So from there up, all the way down to the 227. The 227 obviously is a very small pulley, and it will spin the blower very hard, and that's about the size that we feel comfortable going down to. But what we wanted to kind of get into today was obviously showing you guys what we offer for the blower pulleys, and we also want to get into the engineering aspect of them. And we obviously add a grip technology to the blower pulley surface. So where the serpentine grooves are, you need to add grip. So when you start going smaller, on the pulley, you need to add grip to it because it starts making less surface area for the belt to ride on. So it's more prone to slip. So on a smaller pulley, you're gonna have to do something with it. We came up with a CKP technology, which we call it a convex knurling process. And it's essentially a CNC machining process that puts a groove and path in the serpentine area where the belt rides to allow for more grip. It is a pressure sensitive process for the belt. So as the belt is gripping the pulley and pressuring into the face of the pulley, pressurizing into the face of it, the more pressure and tension that's added to it, the harder it actually grips. So normal driving, when you're not putting a lot of boost into the engine and there's not a lot of load against the rotors, that belt isn't being applied as firmly to the actual surface of the pulley. So as boost increases, obviously the load on the belt is going to increase because the resistance on the blower lobes becomes higher. So you're not going to be as harsh on the belt at normal driving, but as you get into it and you're running the car harder and you're making more boost pressure, it's able to actually grip harder into the surface of the belt. We'll go over that more here when we go up to the shop and kind of show you the engineering and R&D process and some of the testing that we did to help develop these pulleys to the best that we can for the customer. Because here at SPE, one of the main things that we do is if there's any way to constantly evolve and make something better, we're always going to do it for our customer. So that's one of the main things, you know, as far as these pulleys go, that was one of the main concerns that we had with these. Was early on in the design process, the whole reason these pulleys were birthed from the beginning was the fact that we felt a need to do our own pulley because we felt that we could do a very good job and provide our customer with a really solid product. So we want you guys to know why we did what we did and how we kind of go about doing it, so you can feel more comfortable purchasing this pulley and some of the other products that we do. But basically, the whole idea behind doing these pulleys the way we did them was to just obviously give you the best grip possible and give you the best option possible for changing the pulleys on your blower. The 3.2, 2.9, 2.8, and 2.7 are available without the convex knurling process, because obviously anytime you're adding grip to the belt, it is obviously going to wear the belt more. So anytime you're doing, it doesn't matter whether it's a surface treatment process like lasering or whether it's a machining process that we're using here, it doesn't matter. It's going to add wear to the belt. There's nothing that you can do about that. On the pulleys that don't require a lot more grip, because they have more just general surface area in the larger pulleys, you don't need that aggressive texturing. So we offer it both ways. If you're running a larger pulley, but you're also running an overdrive crank pulley or a larger diameter crank pulley, you may still need the convex knurling process or grip process on the pulley, even if it is a 2.7, just because the crank is actually spinning it faster. So that's the other thing. If you have questions on that stuff, you know, we're here to help you. If you think like, hey, do I need that process to, you know, where am I going to be at on my combination? You know, we're always here to help. You can email us, call us. We'll help you out the best that we can. As far as that goes, we're going to go up to the other shop and we're going to show you some of the R&D process and kind of how we come up with what we come up with, and get into some of the nitty-gritty engineering process of these pulleys. All right, guys, now that we're up at the other shop, we're going to kind of go over our 2020 GT500 test rig here for the pulleys. We came up with this because we wanted a more calibrated way and simpler way to basically check grip force on pulley designs. So this rig is based on the accessory drive of the 5.2 motor in the GT500. So pulley placement, even the types of pulleys that are on here, all the way down to the AC clutch, All the idlers, the blower snout, this is literally a 2020 GT500 blower snout that bolts in from the back, and then a machined 8-rib pulley to simulate the dampener. But everything here is exactly how it would be on a car, even down to the stock tensioner. We can even swap this out with aftermarket ones if need be to test things. The reason we did it this way is there's actually two reasons. One of the main reasons is being able to be up close and personal with it and get right at it rather than trying to do something on an engine. And the other reason is it allows us to actually test things in a quicker manner rather than having to only put it on a car and run it on a dyno. Running cars on a dyno to test pulleys, yes, it can work, but the problem is if a pulley's slipping, you're going to see it. You may see an RPM dip or a spike, and a dip or a spike and boost, which obviously you're going to see that on a dynograph. But the problem is you don't have the consistency. The main issue with it is you make a pull on a car, it can get heat soaked, it can be cooler, hotter. There's too many variables. So that was the other main thing we wanted to do with this, was eliminate a lot of the variables when checking this stuff. So what we did is, obviously, it's the configuration of the front of the engine as far as the placement of all the pulleys. All the pulleys spin except for the crank. So everything is able to spin. It's all bearing just like it would be on the car. The crank is locked and pinned. So you obviously, there obviously has to be a way to tighten the belt down so that the belt isn't going to move. But we also need the tensioner to be able to sweep and essentially move like this and allow the pulleys to still move but pull the slack out. So after you put the belt on, crank's being locked in place, we have another bolt here that runs in that locks the belt to the locked crank pulley. So this is your tension point, or your stuck position for the belt. And then over here, like I said, you get the sweep with the tensioner. These pulleys are allowed to sweep, but the belt can't physically slip. It can only slip at the place that you're trying to drive it. And we're going to show you that here when we go and do the pulley test. We're actually going to do a mock-up pulley test on a competitor's pulley and then ours, so you can actually see the difference in some of the things that we actually work against and use for data. So what we'll do is we'll show you the pulleys here next up close and kind of explain some of the nitty-gritty engineering aspects of ours, and then we'll also show you the competitors' pulleys, and we're also going to show you the positive and the negatives of both. Alright guys, so we're going to go over the 3 pulleys here. We actually got out a stock one for you, and then what we're going to do is kind of give you a generalized idea of some of the information that we go over whenever we're making stuff like this. We're going to go ahead and start by weighing. So we're basically going to obviously weigh these on the scale. This is a one-way clutched factory pulley. So these pulleys are inherently heavy just because they have a one-way style bearing in them and clutch assembly. So what we're going to, obviously we'll tear this here. Good, there's your red. Let's see what this weighs. So that's a solid 4 pounds. So we're going to do that. We're going to mic this real quick. So the factory pulley measuring it right on the top of the rib, which is where you measure most pulleys from, is 3.06. So 3.0, I'm guessing around 3.05 to 3.06 is roughly what the factory pulley normally falls within. So it's 3 inches plus around 50 to 60 thousandths. So we're going to go ahead and now actually measure a competitor's pulley, and we'll talk about some of the positive and negatives of their pulley and our pulley. But we're going to get weights and overall sizing off the ribs, because they actually are a little bit different. So if you get a 2.5 pulley from our competitor versus our 2.5 pulley, you know, you are going to get them. They aren't exactly what they say they are. So here's the 2.5 from our competitor. We'll go ahead and weigh this. So that's 11.97 ounces. And we'll go ahead and weigh ours. Actually, we'll do that here in a second. Or do you want to do them back to back, you think? So that's 11.97. And then ours is 7.94. So obviously considerable difference, and that's one of the main things, you know, when we designed our pulley and did our style hub, the main thing we went for was cutting as much weight as possible out of the whole deal. And by doing our own socket with our pulley, we were able to do that. Cut quite a bit more weight off. All right, so we'll go ahead and measure this real quick. So these are, both of these pulleys, by the way, are 2.5s. So the competitor's pulley is coming in at 2.497, and then our pulley, our 2.5 pulley, is going to come in just under that, and I'll explain here in a second why that is. So ours is 2.44. Obviously I'm doing this not 100% proper with this caliper, but ours will be around 2.44, 2.45 for sizing. So our 2.5 inch, just keep this in mind, our 2.5 inch pulley, being that it's about 40 thousandths roughly smaller, you do have a little less surface area for the belt to grab because this pulley is slightly smaller than our competitor's 2.5. The main reason that we did that is because, if you recall here just a second ago when we measured the factory pulley, it was slightly bigger than 3 inches, about 60 thousandths bigger. So one of the main reasons we did that is by changing the size of this pulley a little bit, we were able to make the boost number that you gained across sizing of our pulleys more of a consistent number, as in, you know, as we change to 100 thousandths of an inch, you pretty much get 1 pound of boost. By doing at an exact size at 2.5, you may not get exactly 1 pound of change. So that's one reason why we did that. But just keep that in mind when we move over to the testing rig and we start talking about surface area and where these pulleys are slipping at. Obviously, if you have less surface area on the pulley, this pulley, you know, as you get smaller, it's going to take less force to make this pulley slip on the belt because you have less surface area gripping the belt. It's just general physics. So what we're going to do here is talk about, on our competitor's pulley, some of the positive and negatives. Obviously, it has a grip surface on it that is done by laser, and it does work. One of the main issues with doing a small, one of the negative sides with doing a smaller, more micro surface like this, we'll post up a picture of what happens over time with these pulleys. You know, you have a belt that's constantly riding over this and causing friction no matter what, and this texture actually wears off. This is one of the issues that we found over time with this type of surface. You know, it's longevity wise and under huge power, you know, huge horsepower type situations, or where you're running a small pulley, that's something you're going to run into where you have a lot more potential for slip and a lot more potential for obviously wearing that off if you have something that's more prone to slipping or causes more heat, more friction, etc. So that is one of the negatives. One of the positives of doing this type of surface, and it more leans towards the company rather than the customer, this process is a lot cheaper and that's a lot easier to do compared to, doing axis style machining, which is what we do on ours, where it's just a lot more time consuming to do our CKP process, because the convex knurling process on our pulley, it's just more time consuming. So it can drive the cost of the part up, but that's not why we do this. We do this to create the best possible product that we can. So getting into our pulley, obviously one of the negatives is it costs us a lot more money to do this process, but you're not going to wear the machining process out of this pulley. It's just not going to happen. The way that these knurls are done, and when we machine this pulley, it actually causes, as I said earlier, it causes, as you apply more force to the belt and more load, by the boost pressure that you're trying to make, you have more load against the rotors. It causes the belt to have more force against it. So that belt is going to just naturally want to dig into the pulley more. And as it does that, being that these knurls are actually tapered and kind of fluted, it gives it a tighter and tighter and tighter grip as you apply more and more pressure. Obviously there's a point that stops, and we're going to show you that here on the test rig, but that's the basic concept of it. And with less boost pressure under normal conditions, and you're just cruising down the road with no boost, it's actually able to ride, I don't know if you can see that, how the top side actually has more surface area than the inside of the V. Can you actually get that? Mm-hmm. So essentially, when you have less tension on the belt and less load on this pulley, meaning you're not running boost, the belt can actually ride up on these flats rather than into the tighter, more siped area in the pulley, which will obviously, anytime you're running any pulley that has any kind of a grip surface on it, it doesn't matter, you're going to get belt dust, you're going to get more belt wear, because you're adding grip, and it's a friction surface. There's just no way around that. So just keep that in mind as well. But the cool thing is, if you're driving the car easy, you're not wearing the belt as much. So even under normal cruising with our competitor's pulley, you have constant wearing going on. That abrasive surface doesn't change with tension. It's just always there. It's from top of the rib to the base of the rib. It has the same contact with the belt V from top to bottom. So that's not going to affect or change under any circumstance like it does with ours. One other little point I'd like to make is, on a standard pulley, you can see obviously it's flat on that edge down into the V the whole way. Well, that's what we kind of simulate at the top edge of the V on our pulley with that flat area. That's what's being simulated, is the more smoother side of a factory pulley. And then once you apply that load, it gets deeper into that V, where it gets tighter into the convex knurling, and it is actually applying more tension to the belt as it pulls. So one more thing I wanted to touch on with our pulley is one of the things that we do when we add this knurling to it, in this machine process that we do, we actually angle the machine path. So whenever we put this in here, we're actually angling the tread pattern a little bit, so to speak. And there's a couple reasons for that, and a thought process behind it that we feel works to the advantage when you start getting into smaller pulleys. One of the things, I don't know if any of our customers would have noticed this on any of their vehicles or not, but we did under a lot of testing with Whipple and other types of superchargers. We've noticed, being that the pulley is out on the end of a shaft, as you start spinning that blower faster and faster, and you get to the edge of the RPM that thing wants to be spun at, you're also getting the edge of the strength of the shaft. So you start really pushing everything, bearings, shaft strength, everything. And what we noticed would happen is the end of the blower snouts actually start to flex. They start pulling down. The belt actually flexes the shaft of the blower. And what happens is the belt tends to want to ride out off the pulley because it's flexing down. So with our process, we're actually driving the belt not only down into the V of the serpentine, but we're also kind of driving it back at the same time, just slightly. It's not a lot. It's very faint to the eye if you're looking at it. Not super noticeable, but it does seem to help and keep everything more aligned. So if the pulley does seem to get off track or pull downward, there's less of a tendency for that belt to want to ride off of the grooving and more or less wanting to stay planted in the grooving and stay back to more to the back side of the pulley, which is only going to happen as it starts to, you know, flex and move downward. And obviously this has been tested through and through, so it does seem to work pretty well, and that's why we left it in there. So what we'll do now is we'll go back to the test rig, and we're going to actually show you how we test them and give you the readouts and everything, kind of get into that. All right guys, we're back over the test rig. One of the things we're going to touch on that I kind of forgot to talk about, on any of our pulley systems and anything that we do as far as like testing, as far as just the development aspect of it, even down to our test rigs and everything, they're all done for each platform that we work on. So if we're selling a pulley for a certain platform, this is the approach that we take. And we also obviously own the vehicles that we build products for. So there's no product, not just pulleys, but anything else that we sell, we own those vehicles and we do all of our own testing, and nothing goes out the doors here unless it's vetted and we're fully happy with it. So what we're going to do now is we're going to start with the competitor's pulley. We'll throw it on here, and then we'll get this all set up, and then we'll show you the actual process. All right guys, we'll kind of explain this here real quick. We have the belt on, and it tensions just like the factory pulley and or tensioner would work on the car. And then we're also marking the belt so that we can make sure that when we got the reading that the pulley actually did slip. So you have factory tension pressure with a factory tensioner. We have the belt locked to the locked pulley, so the belt isn't able to move, but the belt is able to tension because all of these pulleys can spin except for one. So you're still able to tension the belt properly. You just take out the things that would throw this test for a loop on the engine. You know, if you're trying to do this test, you have to worry about the crank spinning or the belt slipping on the balancer. All that's taken out of this equation. So we have the belt marked, the pulley marked, and then what we'll do is we'll take a digital torque wrench and we're going to grab this pulley and turn it 180 degrees. And that'll give us a nice sweep. We'll do a nice gradual pull, and then the torque wrench itself actually gives us the peak amount that it sees during that sweep. So we'll show you how we do that here. So when we do that, torque zeroing, that's the peak, but it won't even alarm for that. We shouldn't hit that. So we'll start at 180 degrees. And you'll notice the belt won't move, but the pulley will eventually slip. And we're going to drive it through 180 degrees regardless of if it slips or not, just so we can get a nice clear drag on it so we can see how much we get tension wise. So peak that we're seeing for grip here, it's going to show us once I release this. So that was the peak that we saw on that sweep. So you got 50 foot-pounds. And then obviously, if you look up here, the belt stayed in the same position. And it's about 180 degrees from the mark. So you can see the pulley actually slipped. And now what we'll do is we'll take the competitors off there, and then we'll throw ours on. We'll see what the difference is. All right guys, we got our 2.5 pulley on here. Tensioner all set. Got the pulley marked. So we'll show the same slip, and then we'll go ahead and give this one a spin here and see where we're at. Same thing, 180 degrees. We'll do a nice slow pull here. And then if you get in here, you'll see the peak when we stop. 81.2. So obviously you can see that there's a considerable difference, and as we add that torque and that pressure to it, you can almost see it as those numbers would rise up. They just increase, obviously. What does that make? That makes about roughly a 30, roughly around a 30 foot-pound difference. We'll graph that out for you so you can kind of see the difference and what that looks like on a scale. Obviously it's pretty considerable. So that pretty much covers how this system works for us. Obviously, you know, we do it on the bench like this, and it took us many attempts and different styles of pulleys and machining processes to land where we landed. And obviously we did testing on the cars as well. We work with Palm Beach pretty closely, and Ken gives us a lot of feedback as well, and it's great input, and it also helps us, you know, not just testing here, but testing in the real world. It helps us come out with a better product. All things, you know, that we gear specifically towards our customers and give them the best product we possibly can. So that's it for today. We really appreciate you guys checking the video out. If you guys have any questions on this stuff, you know, from even just how we're testing and you know, anything, email us, call us. We'd be more than happy to talk to you about it. Yeah, so we'll catch you on the next one. Thanks.